Hi everyone. Now, as Lily couldn't join our little video conference, I thought I'll talk you through the last two bits we needed to worry about with simple harmonic motion. Now, I jumped a bit the gun when I talked about energy in simple harmonics, because in your book they first started to look at two classic types of simple harmonic. One being a string pendulum, so a little mass suspended from a string. And as long as your angle here, you pull it off horizontal, is not more than 20 degrees, then the movement of that spring of this pendulum ball is pretty much simple harmonic motion, close enough anyway. The other classic example was our spring pendulum of a mass that's suspended from a spring moving up and down. Now, a couple of pages in your book, they mathematically derived these two equations for the time period of a string pendulum and of a spring pendulum. Now, it's really nice to work through this mathematically. Maths there is a little bit like poetry, and to be honest, the equivalent deriving these equations is the poetic equivalent of a nursery rhyme, but still, it is quite nice. So I'd like you to spend a bit of time trying to follow through those couple of pages where they're deriving those two equations, but I won't do it on the board here because you've got it there and you need to do it in your own time. And in the end, actually, it is not a requirement for the standard. You will have to be able to use those two equations, but I think it's easier if you thought your way through where they came from. Okay, so the period of string pendulum depends on 2 pi square root L over G, L being the length of your pendulum, and G is gravity 9.81. So if you would go to a different planet, gravity would be different, and the period of that pendulum would be different too. One thing to realize, or to make sure you understand here, is that there is no amplitude in this equation. So the period of the pendulum is actually independent of the amplitude, as long as you don't go too far up and increase that angle anyway. Same here. For a spring pendulum, the amplitude doesn't affect the period, only the mass of the object and the spring constant. Remember, I'll still have it here. I've shown you this little ceramic chicken on a spring. So here I can use this equation to observe and to derive whatever I want from here. Let's do a little exercise here, okay? Now, if I worked out the spring constant here by attaching my spring to, I've got one little spring balance here, and I worked out I need to extend the spring by 13 centimeters, and then my spring balance shows a force of 10 Newton. So my spring constant, equals 10 Newton for 0.13 meters. That will give us a spring constant of close enough 80 Newton per meter. Okay? I've also timed my little chicken roughly, and I've worked out that the time constant, the time period equals 0.56 seconds. Okay? Now, I told you guys that anytime, we get rid of this side now, that at any time an object that's performing simple harmonic, the energy total equals kinetic energy of the object oscillating plus potential energy. Now that means that the total energy will be equal to the maximum kinetic energy, because at its maximum all the energy of the object oscillating will be in the form of kinetic. Kinetic energy is 1/2 mass times velocity squared. Now velocity, I hope you remember, velocity equals a omega. That's the maximum velocity of an object moving in a circle or performing a simple harmonic. So therefore I can write that as K equals 1/2 mass times a squared omega squared. Okay, so that's a useful equation, and if I tell you that I've got a time period for my little chicken on the spring of 0.56, if I have a spring constant of 80, and if the displacement A, let's say that was 5 centimeters, 0.05 meters, with that information, you guys should be able to work out a couple of things. I would like you guys to work out the mass of the object, of my chicken, and I actually would like you to work out the energy total of my system, the oscillating chicken. Give this a go. Pause the video, because I'll soon add the second part of this video will be the answer. Okay, so here we go. We've got an object suspended from a spring. We know the spring constant, 80 Newton per meter. We know the time period, 0.56 seconds. And we know the amplitude, 0.05 meters. We want to work out the mass of the object, and we want to work out the total energy stored within the system. Let's start with the mass. Quite obvious, this equation for the time period of a spring pendulum will help us here. 2 pi square root m over k. The only thing we don't know here is the mass, so we can resolve that equation for mass. P squared equals 4 pi squared mass over spring constant. Therefore, T squared divided by 4 pi squared multiplied by K equals mass. If we put in 0.56 for the time period and 80 for the spring constant, we work out that the mass has to be 0.64 kg. I hope you managed to get the same result. So, how do we work out the energy of the system? As I told you, the total energy, ET, equals EK max, the maximum kinetic energy. I can work out the velocity of my object. V equals A omega. Okay, therefore V equals 0.05 times 2 pi over 0.56 seconds. That gives us a velocity of 0.56 meters per second. And that equals here that's my maximum velocity. Therefore, 1/2 times mass times velocity squared equals 1/2 times 0.64 kg times 0.56 meters per second squared. That gives us pretty accurately 0.1 joule. I hope you managed to find the same result, or maybe I made a mistake. Then please find the mistake. Okay, I hope that worked. You should be now able to do those the exercises to those last 2 paragraphs in your textbook on simple harmonic. Any problems, as usual, just flick me an email. Good luck and goodbye.